Welcome to the Explainer. Okay, today we're not just staring at code or, some abstract cloud architecture diagrams. We are literally going to deconstruct a digital bank heist. Step by step, we're going to analyze exactly how an attacker maps out a target, finds a tiny crack in the armor, and systematically escalates their privileges until they've walked away with the keys to the entire kingdom. We are looking at the Kubernetes kill chain.
But before we get into the nuts and bolts of the heist, we kind of need to ask a slightly uncomfortable question. Is your Kubernetes cluster actually safe? A lot of engineers sleep pretty soundly at night because they assume that since their apps are running inside isolated containers, or pods, they're just inherently protected from the outside world. But as we're going to see today, isolation is absolutely not the same thing as security.
Because there's this huge gap between what builders believe and what attackers actually know. The engineer's myth relies on this idea of perfect isolation. But the hacker's reality? It's way more pragmatic. In real-world breaches, attackers don't actually need to break Kubernetes itself. They just need a perfect storm of small errors. We're talking one single application bug, plus one configuration mistake, plus one leaked token. You string those three little things together, and you go from a single compromised pod to a full cluster takeover.
So, here's our heist blueprint for today's Explainer. We'll start with Kubernetes structure and myths, then look at the initial pod breach, stealing the identity token, lateral movement and takeover, breaching the etcd vault, and finally, how to actually stop this attack chain in its tracks.
All right, Section 1, Kubernetes structure and myths. Every good heist movie starts with the crew laying out the blueprints, right? Let's get a feel for our target environment. Let's look at the outer perimeter. A Kubernetes cluster isn't totally walled off. It has doors. Traffic flows in from the wild west of the internet, passes through the ingress, which basically acts as the front desk routing traffic, and then directs that traffic straight to individual pods. And these pods are your worker bees. They're the ones running your actual web applications. But deeper inside the building, we have the control center. Your worker nodes don't just act on their own, they report directly to the API server. Actually, think of the API server as the bank manager. It controls all permissions, checks every ID badge, and routes every internal request. And sitting right behind that manager is the etcd data store. That's the vault itself. If you can talk to the API server and trick it, you are literally one step away from the vault.
Okay, Section 2, the initial pod breach. How does the bad guy actually get into the building? Well, attackers rarely go after the Kubernetes infrastructure directly at first. Instead, they go for the softest target, your web application. Let's say a developer wrote a Python app and used a function to process user input, but forgot to sanitize it. The attacker exploits this remote code execution vulnerability. With just a few lines of malicious input, they bypass the application logic completely and drop right into a basic bash shell inside the pod. Now, they usually start out with really low-level privileges, like the www-data user. So they're in the building, but they're basically just standing in the lobby.
Now that they've got a foothold, we enter Phase 3, stealing the identity token.
You'd probably think the hacker immediately starts hunting around for customer data to steal, right? Nope. They look for credentials, and this brings us to a frankly shocking default behavior in Kubernetes. By default, it automatically mounts a service account token right inside the pod. It is literally like a company issuing a master keycard and just taping it under the reception desk for anyone to find. An attacker just has to peek inside a specific local directory, and boom, there it is.
So what's actually on this stolen keycard? Well, if the attacker opens that directory, they get three things: the token itself, the namespace information, and the certificate. Armed with this ID card, the attacker is no longer just some random anonymous process running in a container. They now have a verified identity that they can use to walk right up to the bank manager, the API server, and start making official requests.
Which brings us to Section 4, lateral movement and takeover. Our hacker has an ID badge. Now it's time to see exactly which doors it unlocks.
The crucial point here is how they test these permissions. The attacker simply queries the API server. They are checking the internal role bindings to see what actions or verbs they're allowed to perform. If they see verbs like get, list, watch, or, worst of all, a wildcard asterisk, which basically means allow absolutely everything, they have hit the jackpot. With an overprivileged token due to a simple RBAC misconfiguration, the attacker can instantly map every pod, every node, and every single namespace across your entire internal network.
Next, they go looking for the really good stuff. They query the system for secrets. And this brings up a classic bit of IT naming irony. We call them Kubernetes secrets, which sounds incredibly secure, right?
But they are actually just base64 encoded plain text. They are not encrypted at all. If an attacker finds your AWS keys, your database passwords, or Git tokens, all they have to do is run one simple decode command. Instantly, they have your true unencrypted passwords.
Now, if one of those tokens happens to have cluster admin privileges, the situation goes from bad to critical. The attacker can now create their very own malicious pod. They inject configurations setting things to privileged, true. Then they execute a host path attack by mounting the root path directly into their container volume. In plain English, they just shattered the container isolation completely. They bypassed the pod entirely and took root control of the underlying Linux host operating system.
The attacker now owns the host machine, which brings us to the final target, Section 5, breaching the etcd vault. And this is where the heist is officially completed. The etc data store is the true crown jewel of Kubernetes. It's the brain. It's the distributed store that holds the entire state of the cluster. Every password, every service routing rule, every single role binding, it's all right here. If a hacker can read etcd, they see your entire universe. And worse, if they can modify etcd, they can quietly rewrite the rules of reality for your cluster, creating completely undetectable backdoors. It's game over.
Let's just take a step back for a second and look at the path we just walked. It builds a terrifyingly clear picture of a real-world attack chain. It almost always starts the internet with a simple web vulnerability that grants a pod shell. Once inside, the attacker steals that automatically mounted token, uses it to authenticate, exploits a misconfiguration to read your secrets, takes over the worker node, and ultimately compromises the vault. It's a ladder, and the attacker just confidently climbed every single rung.
But hey, here is the good news. You can break this ladder. Let's move to our final section, stopping the attack chain.
Defending Kubernetes isn't about buying some expensive magic security box. It's about breaking the specific links in the chain we just talked about. First, enforce strict least privilege RBAC. Never, ever use that wildcard asterisk. Second, flip one simple switch in your config. Set auto-mount service account token to false so that master key card isn't just left sitting on the desk. Third, use pod security standards to strictly ban privileged containers. And fourth, lock down your internal traffic with strict network policies so pods can't just talk to whatever they want.
Now, for a truly hardened environment, you need advanced defenses. Never store plain passwords in standard Kubernetes secrets. Integrate a dedicated secret management tool like HashiCorp Vault instead. And lastly, you absolutely must have eyes on the inside. Deploy runtime security tools like Falco or Cilium. These tools sit in the background and act like internal security cameras, instantly alerting you if a suspicious shell starts up inside a pod or if a sudden privilege escalation happens.
So, I want to leave you with this final provocative thought. The vast majority of Kubernetes breaches do not happen because Kubernetes itself is fundamentally broken or insecure. They happen because of overprivileged service accounts, a lack of internal boundaries, and vulnerable applications. Hackers don't break Kubernetes. They just walk the permission chains that you left connected. So take a look at your own architecture today and ask yourself, where is the weakest link in your chain? Thank you so much for joining this explainer, and stay secure out there.